All right. Welcome to this session about stream processing and Flinks and Kafka Streams and all things around this. Just curious, how many of you using Kafka? Because this talk would be heavily, how many of you not using Kafka? Okay, few people. How many of you using like alternative solutions in the streaming world? Maybe Pulsar, maybe Kinesis. Question to you, why? But anyway, this talk would be solely focused around the concept of Kafka, because obviously Kafka Streams, obviously for me, and it will be obvious for you at the end of this presentation, Kafka Streams is very tightly coupled with Kafka, and Apache Flink can be used with some alternative solutions. So some of the concepts that I explained here can be also applied somewhere else. Every time when I talk in the talk about comparing certain things, I kind of trying to come up with like some, the funny pop cultural reference. I was thinking that maybe play kind of like a Rocky IV, like a Drago versus Rocky, because Dolph Lundgren is from Stockholm, kind of will make sense, right? No? But I also realized that in the Stockholm airport, there's no photo of Dolph Lundgren. And I was trying to say, like, why? Like, Joel Kinnaman is there. Like, why Dolph is not there? He's not that popular in... Yeah. Not that popular? What about Max Martin? Like, the person who wrote basically all pop cultural, hits since 2000s. I also haven't seen him there. So that's also, I don't know, I don't understand. Find me after and tell me why. My name is Viktor Gamov. I work as a principal developer advocate at a company called Confluent. And I am a Java champion. I know quite a few things about Kafka. So I wrote the book about this called Kafka in Action. If you want to pick it up, find me. I give you a discount. And I'm going to be talking about things that I love from perspective of technology. It's not AI talk, Unfortunately, yeah, it's a bummer because there would be a lot of people who will be talking about AI. It is very heavy, code intensive and the concepts intensive, right? Again, basic prerequisite is that you know at least some of the concepts of Kafka. I skimmed through this very quickly because some of the things that important in Kafka architecture will be important in our conversation today. So I'm going to start by introducing the concept of stream processing. It's easy. So how you will explain this for someone? So what we're going to be dealing with? So stream processing is the tools or like a set of the practices that allows you to deal with events or data that constantly arriving, and there's no end. For all intents and purposes of this particular talk, and in general, when you will be talking to me about Kafka, we can assume that batch use case it's just one of the subsets of streaming use cases, because a batch use case is just like your data already arrived. In the streaming, there would be few other things that needs to be taken into consideration. Speaking about the time, that would be time of arrival of the message, or maybe there would be some late events or something like that. And the Kafka would be cornerstone component of stream processing, because Kafka is an event streaming platform. It is a distributed transaction log, if we want to go in details. And Kafka will be storage. So we will be reading data from in and out in Kafka. Each message will be represented in Kafka in a format that will include multiple things. You always writing into the end of the Kafka log or the partition, how we call it. You never modify message or event. If you need to modify, you need to submit a new event. The messages will include some additional metadata, key value. So key will be used for certain things like a grouping, or if you will be looking at a low level, it would be a thing that will be responsible for coordinating where these messages will land. Timestamp is important when we need to extract the information about the time when this event was either ingested into Kafka, because this is timestamp would be automatically created if you submitting message to Kafka. There's some other ways how you can do this. We're going to talk about this a little bit later. We're going to talk about timing semantics. Topics, logically, only exist logically because all the data will be stored in partitions. Partitions will be represented as a set of files that's stored in file system. You can have multiple partitions per topic. This is how we achieve scalability in terms of reading data and how many messages we can read or how many consumers can consume messages for particular topics. Two components that are very important for Kafka. It's a producer and consumer. Producers will send a message to Kafka topic. We're using keys in the Kafka messages as performing routing, where these messages will land in the Kafka partition, or which partition. And the producer implements very important concept called idempotency, which is prevents of producer to generate duplicated messages. Meaning that in case of some of the failures will happen, not in your application code. If you want to submit two messages in your application code and they will be duplicates, it still will be recorded in Kafka as a duplicate. But if you try to submit one message and there was some network glitch and some of the logic inside the Kafka producer will decide to resend this message, that in the past, before the idempotency was introduced in Kafka, might create some duplicates because you might not receive acknowledge and you try to submit second time and the server or broker already committed this into log. Now duplicates will not be generated. This kind of like when theory of beautiful streaming hits the reality, because in the reality we're still dealing with some of the concepts from the real life, and specifically how the message is structured inside TCP protocol. So those things are not exposed to application code, but rather something that we implemented on the producer side of things in order to increase, say, throughput. If you want to submit multiple messages, maybe it will be a good idea to send them in batch. But order also will be preserved, so no problems here. Same thing with compression if you need to implement something that will effectively send the data over the wire. Producers will submit the messages if there's no key on the round-robin fashion, or if there's a key, particular message will always land in particular the partition. Why it is important? It is important if you're trying to do some sort of implementation of transaction processing, and you need to make sure that all transactions, one particular credit card, will be ordered in the same place. If you have two transactions on the same credit card, you submit them to the producer, they will land in the order how they will generate it. Now, what do we see here? Yes! That's correct. That was AI generated, because before that I was using some National Geographic picture that I don't know where was the source. Now it's safe to use it. But also, what actually we see on the picture, like things. Nest, okay. What else you see? Consumer group, okay, we're getting somewhere. Okay, someone already got the idea. This is the way how I like you to remember about consumer groups. So Nest is a consumer group where we have multiple consumers. Those little cute little birdies, they are our consumers in our application. And this big mommy bird is our consumer group coordinator. Special component that sits inside the broker and will be responsible for distributed load between these consumers. So this is an important slide because it will give you an idea how Kafka implements and Kafka Streams implements scalability, and Kafka implements kind of like a fan-out logic for increasing consumption speed. Mommy bird can bring 1, 2, 3, 4, 5 worms. So each of these individual baby birds will get each worm. Same thing is the mommy bird or like consumer group coordinator will provide to a consumer group a topic with 5 partitions. We have 5 consumers. Everyone will get its own partition. What's going to happen if we will have another baby bird hatching? Like in the same situation. See? Yes, the consumer group will consumer will idling, but baby bird will be starving. Yeah. So what happens in the opposite side if one of these baby birds will fall out of consumer group? Exactly. Consumer group coordinator will rebalance. This is a process that's known as consumer rebalance, and consumer group coordinator will reassign this another partition to another consumer. So this is very cool. This is multiple things we see here. It's how scalability happens and how the fault tolerance also happened on the Kafka side of things. Regardless if that we have in Kafka messages by key and value, you cannot do a random search by key and value. You need to have something where you can read this, maybe reinstate. If you want to do query point on type query, you need to have somewhere you can maintain store, but you cannot directly do key value search in the consumer side of things. The way how applications will be doing this, I'll give you another example. It's another AI-generated image that will have book and bookmarks. So you might have multiple different use cases, but since data will be available to anyone, any consumer, assigning different consumer group name essentially allows you to create new application types. So in this particular case, I have 3 friends. They're reading books. One of them, it's me, I'm dumb, so I'm only interested in looking for pictures in this particular book. So I have a stream of pages, and I'm processing, I'm scanning through, and if I will find the picture, I will do something. I maybe do the copy of this picture, or maybe I tear down the list. No, I cannot do tear down the list because I need to create kind of like copy anyways, because we established in Kafka everything is immutable. Now, Robin is doing something much more smart. He might be counting words, and after that he needs to find, at the end, needs to give me a table of how many words happened in this book. Like say word book, 1,000 times. Word strawberry, 300 times, or something like that. And the team, he is kind of like very interesting in finding definitions, or maybe going through thesaurus and finding words that will be representing, or like find the synonyms and stuff like that. So team essentially performing what we called the stream to table join. He going through the stream or inside the book, and they're trying to create new stream that will have expanded version of this book, which every word will be replaced with the word from thesaurus that will have a synonym. So in this picture, we can see like multiple different applications depend on their the actual task that they're trying to do. They will be somewhere on this journey through this log. And that's why we have a bookmark here. Each bookmark will represent a consumer group offset. So offset, this is the place where all these applications would know where they stop, or what they processed the last time. Okay, so we're done with Kafka. Now we're going into world, beautiful, fascinating world of stream processing. We established that Kafka, our store of our data will come from Kafka. And today is very safe to say that technically, or like virtually, data can come from anywhere because of the connectors available. You can do whatever data you push into Kafka. So let's talk about the architecture of applications that you will be building, or systems, because we're going to be talking about 2 things, where Kafka Stream is a library and Flink is a framework and the whole system to build. Let's take a look on the Kafka Streams architecture first. In this diagram, we can see multiple different elements that involve here. So as the name implies, Kafka Streams is something that comes together with Kafka. It's the framework that comes, call it like in-store brand, right? You have a something, or like Kafka comes with some stream processing framework, like batteries included. We do have something that runs our Kafka. There's a bunch of different topics, and we create a source stream inside my Kafka Streams application. Kafka Streams is a library. It's a JVM library. It's a jar. You drop it into your public static void main application, or you can drop it in something that like Spring Boot, Quarkus, whatever. These frameworks already have integrations. You can just enable by adding dependency, and now your Spring Boot application will have capabilities to do stuff with Kafka. Inside your application, you have a whole logic of this, like parsing, this topology that will be representing the way how you transform. transform data and how you will be dealing through the different stages of this. Underlying technology will create threads that will be talking to Kafka topics, to read data, write data from Kafka topics. When I was talking about this use case about book, it was not just to do quick lulz and giggles. It's tough crowd, I understand. Okay, I'm still working on this. But I showed you examples of two types of stream processing. When I was talking about Viktor, who's reading book just to find the pictures, it's a stateless stream processing, meaning that it will not require for to give answer of whatever task we're performing. We don't need to know any past because we're going through the page, filtering, mapping, any type of transformations. It's the stateless stream processing. Anytime when we need to perform or have a knowledge about the past, specifically, we need to do grouping, aggregation, any type of join, windowing operations. This is the stateful stream processing. And both these frameworks, one library, one framework, they support this concept of stateful stream processing. Kafka Streams implements this very clever ways. We're going to talk about the state. How it's done, and all these things are basically hidden from you in this application. Before we jump into Flink, let me quickly show you how we're looking into. Say, I have the use case where I do have Kafka topic that includes information about flights, and I want to use both frameworks like Flink and Kafka Streams to do processing of these flight delays. By the way, how is my font and my black background? Thank you. I got a thumbs up from the perfect. Now, the way how it's done with Kafka Streams and Kafka. I'm sorry. I opened Flink and see something is not correct. Yep, that's better. We are. Can perform multiple things. So this is the example of stateless stream processing, because we need to get stream of events and turn it into something that we can deal with our application. In this particular case, I do have the bytes that will represent JSON object. And now I need to turn it into whatever I'm reading from Kafka topic and turn it into Java object so I can deal with this during application. And in this case, we have like a flight stream, and this flight stream will be used next. And this is example we getting from the flight stream. Now we implementing stateful operation. In this particular case, we don't know in what order these events landed, but we really care about, since we're interested in particular flights, because we're going to be doing some of the calculation of flight delays, we need to know some modifier. Maybe it was route ID in our particular case that will define particular individual flight. So we need to make sure that all my flights for particular flight event will be collocated on the same partition, because inside the Kafka, when it was produced, I have no control. So that's why I created this grouping operation that will produce another stream that will include the messages that were they have a key as this flight event. Next thing is that I'm only interested to perform computation on top of a certain sliding window. In this particular case, I have a window of 15 minutes and with grace period of 1, and it will advance. This window will be advancing every 1 minute. And after that, I'm performing this aggregation operation in this particular case, in this function. I will be storing result of this aggregation in state store. So I also can access to this data inside this application. I will talk about state store in a few more seconds. And the way how we can, writing data back to Kafka, so we can say the alerts about flight delays, we perform all the things, and after that we converted this the table that will include aggregates, and we dump it into, where's the alert stream? Yeah, alert stream. Yes, this one. yeah, alert stream that will include some of the information. It can also, submit the log message about the delay alert and things like that. So a little bit some basic aggregation. There's nothing really special here. For a Flink, and again, this is the simple, where it should be something like public static void main application, something like this. So basically, this is how you. Oops, not the Flink. Where's my Kafka stream? Basically, this is your application of Kafka streams. You have a public static void main. You don't have to do anything else, and it will be just working. It works with containers, works with fed jars, works inside the application server, whatever. Now, let's talk about Flink processor now. A little bit before we jump in. Flink, I didn't show you architecture, and no one corrected me, which is. You should keep me accounted for things that I'm talking. Now, slightly more complex things, and the reason for that is that Flink is a general purpose system. So Kafka Streams is the specifically built for doing stream processing in Kafka. Flink is a general purpose system that can use Kafka, Pulsar, the Kinesis, S3, the Postgres, Rabbit, whatever you have. There are some connectors, virtually connectors to any system available. And also, it's designed to be executed in a clustered environment. So it is a framework for building clusters, for building systems. So there would be some of the smaller things that we need to pay attention in this regard, in terms of how you're going to deploy this. There's a component called Job Manager, our application, our Java public static void main application, or even curl. I will explain why. Interacts with Job Manager. Job Manager will read this jar file, or it will read some of the bytes that were sent over the wire. It will understand that it's a data stream API. And after that, it will compile this into some internal representations where we have different operators. And this job will be sent to components called the task manager. Each individual instance will be executed on individual task manager. Inside the task manager, there is more granular control. Each individual task will be executed in the task slots. You can configure resources. You can limit some of them resources. You can change this. It's very flexible. And very important that nodes, they also talking to each other. That was really not the case in the Kafka streams, because each individual instance of application, they don't talk to each other. They don't know they existed. Same thing as the consumers. Since they're sitting in the same consumer group, they don't know that they existed, and only a consumer group coordinator will be responsible for sending that. So Kafka stream is more like a shared nothing architecture, where a metadata will be sent by for broker component that will be responsible for updating this information. In the Flink, since Flink is the general purpose system, those things are applied to any type of system that you will be processing data from. And different connectors, as I mentioned, you have a Kafka topic file system. You can write source, the custom connectors. Results can land in Kafka if you want. Results can write in file. You can write it back to database immediately if you need to have ability to consume this. Essentially, the job manager also allows, there's a REST API that allows you to just submit to the jobs in the format of kind of like a shaded and fed jar. You usually not writing code on the job manager or like task manager, using the data stream API to describe the actual task. So let's take a look quickly on the Flink side now. One of the things that I mentioned in a Flink processor, this is not the application that you will be debugging. So this is the piece of code that will be interacting with Job Manager and submitting actual data stream API topology. So as you can see, I can configure or send configuration for a particular job, but in the real life, the processor would look something like this. So let me, there will be multiple different things that you need to describe. And again, even though it's a public static void application, this is code that would be after command was execute, will be send the thing into Flink cluster, and we'll execute it there. Any Hadoop users, survived Hadoop users, recovering Spark maybe? Okay, a few more, but also good. Hopefully next year will be all Flink users, I hope. So essentially, it is very much the same if you ever done with any type of distributed processing frameworks, and that's why I mentioned Hadoop here or Spark, because they operate in the same kind of client-server model. Through this configuration of the jobs, I can configure things like checkpoints. I will talk about the checkpoints and stuff. In Kafka Streams, we don't need to do anything. We just need to configure this once and say stream from, and after that, name of the topic. In this particular case, we need to use the component called, in the Flink particular case, we need to use a component called the source and sink connectors. We defined how we read the messages from Kafka topic, what we're doing with this. So in this particular case, we define this custom deserialization schema. Another interesting component, another interesting point that we need to make. Since in Kafka we have a key and value inside the message, Kafka Streams essentially takes this abstraction and brings this as a part of API. So we have a keyed streams, even though there might be nulls and stuff like that, but we do have this built in API. In Flink doesn't care if you have a key and value. So we need to tell somehow. We need to tell somehow Flink that we are dealing with some of the keyed values, so we can define the schema of the message and what we need to extract here. So, for example, this is how we only start reading. So we already created this the connector source, and we're saying, okay, we're reading from the source with the watermark strategy. Very similar how we have a time window. Inside Flink, we have a concept of watermarks. What is watermark, Victor? Glad you asked. Watermark is something that, again, will not be exposed to you through your application code. You will not be seeing those. It is a way to Flink to signal to downstream processor that, hey, we are having some of the data that needs to be distinguished somehow. Maybe it was some of the window function that we need to do. So this watermarks, when the Flink will be reading this source stream, and they need to pass this information downstream, watermarks will be added as something that only Flink processors will be able to see. So in this particular case, we need to say watermark for the same. We're showing that the information, the way how to extract information about the time, we're extracting from the timestamp because this was built inside my object. We also can define the timestamp extractor, so it will read this from Kafka message. Kafka Streams by default reads the data from Kafka message, from Kafka metadata, but also you can define timestamp extractor, so Flink the Kafka Streams knows about this. Now, this is where we need to transform this and tell Flink that we do have a keyed stream. So as a result of this operation, key by, we're extracting the key from actual message. Now we're applying the windowing function and do processing logic. Let's take a look here. That already will include key, will include some values. So we start, do logic for our processing. Same thing as we did with Kafka Streams. All right, but I digress a little bit. Let's talk about state management now, because I'm jumping there too quickly sometimes. In Kafka Streams, the simple way how I can explain you state management. So you have your Java util map, and you're trying to write some sort of processing and using the map as your storage. So like every time you need to get back result of aggregation, or maybe like a sum of elements, or maybe some average, you need to store it somewhere. So Kafka Streams provide you with like a very simple interface that you can say materialize to, and it will create a state store. So state store is a Java object. By default, it will be backed by like small embeddable database called RocksDB, and you will be able to expose the state through your application. So that's why very very common use case. You have a Kafka Streams application runs inside something like a Spring Boot, and you need to give a result back in the form of API call. So you can expose your state store that will include some intermediate data, not send this back to Kafka. So you just expose it through think what we call interactive queries. So Kafka Streams allows you to query the individual state of the application. It's not something that kind of like gives you ability to have a built-in database. It's more like a key value store. In Flink, the state is stored inside the special type of binary backend, and there's two types of the state that you can deal with. With some save points, you can submit this commands to your cluster and saying, hey, we want to restart the cluster, so we need you to save whatever you're doing. And after that, we're going to restart the cluster, and we will recover from the latest save point. Checkpoint is something that the Flink system will be automatically doing on some of the regular periods of time. So it will have some sort of incremental backup capabilities. And we need to query the state. You need to either have a sync to somewhere. For example, you have a sync to Redis, and after that, you start querying the stream. There was a concept of queryable state in Flink. It's still there. As far as I understand, it's more or less deprecated right now until the committers will decide to, what to do with this. So there's no direct comparison between interactive queries in Kafka Streams and queryable store in Flink. Now, the topic where we talk about Flink, where I've showed you code. So now the scalability aspect. Kafka Streams has very intimate connection to Kafka, and a lot of architectural decisions that were made to be implemented in Kafka Streams were inspired by the way how the Kafka doing things. So essentially, the scalability happens per partition. Every time we're writing this a topology thingy into in our code, this topology will be executed on each partition. So, like I said, it's a shared nothing architecture. So no other threads will be kind of competing for particular partitions. Just only one consumer can consume at a time, even though one consumer can consume multiple topics. The instance of application can consume multiple partitions, or say you start in one application, you have 4 topics. It will create 4 tasks that will be not necessarily mapped directly to threads. It has its own threading model, and there's the way how you can configure tasks. If you want to scale, you start another instance of this application, and when application will come online, it will talk to Kafka broker, will take information from consumer group coordinator, and information of this consumer group will be propagated, and partition assignment will happen with Kafka Streams application. It's very simple, the way how it's done. The consumers don't need to have anything locally to remember. Everything will be stored inside the Kafka broker. Now, the way how everything will be scaled in Flink is by task managers and assigning the numbers of task slots. So we have jobs that will be distributed, and in this particular architecture, it might or may not know anything about Kafka partitions and things like that. So a little bit knowledge required from operator who is submitting in order to how much resources you need to get for one particular task. You can define the level of parallelism, but it will be depend on particular implementation of particular sync. In Kafka, you can define this configuration in Kafka sync in Kafka source. Now, let me quickly show you some of the things. Let me see if I do have I have a Docker Compose. Do I have it here? No, I don't have a Flink to show you. So in my processor, only thing that I'm configuring here is the checkpoint, but also when I start in Flink, this is where I will be defining. Let me see if I actually have the example of this. I'll show you how it would look like. say if I would do something here. So I would start two components. I'll start the job manager as my separate container, like whatever, and inside task manager, I will be able to define number of task slots. I can start this by scaling task managers. And they will join Flink cluster. But inside the task manager, the way how I can define where all these things will come from, I will be defining as a time slots. Another thing that I didn't mention, but also very important to know, is that in terms of scalability, sometimes you might find yourself in if you will be Googling things and if you will be reading Stack Overflow, you will find or trying to compare Flink and Kafka Streams. Some people might complain about, oh, you know what? In the Kafka Streams, you don't have you have problems with you when you're starting application or restarting application, and your state is too big, and so far and so on. And there's some ways how you can deal with the faster recovery times. And one of the things that Kafka Stream has this concept of kind of standby replicas, to the point of, I don't remember which gentleman we would talk about birds, and it's not starving per se, but it doesn't do any processing. It's gonna start another consumer that will not be consuming messages, but through the same task, it will be just accumulating data in saving somewhere locally. So in case of failure of one of the nodes, this node will take over, and you don't have to wait until it will recover state, because the state will be in the background dynamically populated. And with your Kafka Streams application, in your properties, this is how you define your how many tasks would be running per thread and stuff like that. So everything would be in configurations. Now, we're dealing with time more than we actually, knew. So the windowing operations on those systems are very important, and we need to have ability to deal with event time, when this event was generated on the local system, when it was ingestion time, with a log time, when it was written, when it was processed, and things like that, and all these things. So it's important to understand how the windowing works. Now, in Kafka Streams application, we have a state store. Think about the state store again. It's your key value. You will have, say, Java object, Java map. That's your state store. Now, with Windows state store, we're actually adding one more dimension that will be defining the window size. And we will have our key value, and now we will include the time window where this window will belong. So that's why I like to say, when you're dealing with stream processing, your batching use case is basically this, one of the windowed use case where you know where it ends, when it starts. So that's why Flink can, don't distinguish streaming versus batch. So with the window store, you also can query based on the certain window, if you know what was happening there, and you have this aggregation per particular window. I already showed you the code. We're gonna return this one more time to point this out. Now in Flink, we do have this concept of windowing as well, and also it's implemented on top of this idea of the watermark. Watermark will define when it starts for a particular window, when it ends. And the downstream processor that will be relying on doing aggregation on top of the particular time window, they will read this information. And there's also a way, because the timestamp information will be passed through multiple operators, plus it is stateful through the checkpoints and all this kind of stuff. So you will be able to define the late events processor that allows you to deal with the events that arrived not in time. Just quickly show you how this one more time looks like. In the Kafka Streams, we do have ability to create, say, where is it? Kafka Streams, delay processor. We defined the window, and also we have this is our state store, and this is our how we perform query on top of the windowed stream. So in this case, API allows us not only create those windows, but also kind of some sort of like navigators in downstream operators. In the Flink side of things, there's a ability to create the different type of windows, and everything will be handled, and the watermark generator will include all this information. The most exciting part, exactly once. Anyone understand exactly once? Exactly once is easy, right? It's some controversy I know in the community. So who believes this bullshit? All right, few people. Okay, that's was the general reaction when in 2018 when we introduced the exactly one semantics inside the Kafka. People were just like, no, it's not possible because distributed system. If you've been in the distributed system world, there's always some sort of like a trade-offs, and the explaining like semantic of something is also very important. That will put the context. Now, exactly once is the concept that many people understood incorrectly. So exactly once, it's not like you produce message once, it went through Kafka and processed once. It's not like that. If you thought about this, who thought that like this? Okay, my crowd, the people know this. But in some other places, people still think that this is kind of like the process, the produce, process, and consume. That's the exactly once. Actually, it's another way around. It's consume, process, and after that produce. In this circle that operates basically like Kafka streams, we need to, in one shot or in one atomic operation, and I'm not calling this transactional operation because the words are matter. In one atomic operation, we consume message from the topic, we perform something, some computation, we perform either filtering or we perform any type of aggregation, and when we send back to either as a materialized store or underlying like stream, this operation, if it fails somewhere in between, it will start over. It will not produce partial results. So essentially, the transactional boundary from perspective of how it's implemented inside the Kafka. Producer can produce multiple topics in the same time in a single transaction. And this is what we're using in Kafka streams when we need to deal with things like a state store, with things like the multiple topics, because we can, from one topic, we can do multiple branches of particular stream, so we can do this right down to multiple topics. So these operations needs to happen in one shot, meaning that it needs to be written in multiple topics. And through the transactional processor producer that can write into multiple topics, this particular subject requires talk by itself, but for all intents and purposes of this presentation, in Kafka streams, you just need to go enable exactly once true. That's it. So you don't need to do this. And one of it basically was the reason why exactly once was introduced in Kafka. So it was Kafka streams. Some can disagree, but I do believe Kafka streams is like reference implementation why this exactly one semantics was introduced in Kafka. Kafka streams exactly one semantics handles offset management, so the offset will advance only in case of the successful the atomic operation will perform. It also spans into state store because through this operation we're writing into state store some of the results. Even though it will look like the database transaction, it is not. There's some other things will be done, and yeah. So those things are already handled for you. So the only thing that you need to do is just enable this. And I think since version, no, I don't think it's default, but it should be default because it's no-brainer. Now, in Flink, since it's a general purpose system, there's no one answer that will fit every possible use case. So in this situation, in situation of Flink, that the multiple components needs to be involved. Specifically, the operators that will be consuming and producing data into underlying sources. So source operator and sync operator that will be talking to Kafka sync and Kafka source, they need to be aware about all this, exactly once nonsense. Plus, throughout all this data stream API job, you need to span this transaction. Flink provides multiple the primitives for developers to implement this semantics. I think Kafka source and Kafka syncs, they now support end-to-end exactly once semantics. Some other sources and syncs, you need to check their documentation if they can work together with all this jazz. It also includes information about the checkpoints, and it also will be stored in case of failure. So this is everything is like end to end. Now, you was thinking, cool story, bro, but what I should use. And I will give you this answer. Again, there's no right or wrong answer, so like each individual projects will require its own kind of consideration to the things. Use Kafka Streams when you're writing event-driven microservice. You're writing Spring Boot application, you need to read the data and do something with this in Kafka, and after that show this through the API. Use Kafka Streams. It's easier, it's integrated, deployment model is straightforward. It's cool. You can deploy this in the containers, you can deploy this jar, application servers, whatever you have. Easy testing. I didn't show you, but if you will go to this GitHub repository, it's called the Camusa/stream comparison or something like that, you can find that Kafka Streams has a very cool component called topology driver, topology test driver that allows you to write tests without having Kafka and testing your topology without running this through Kafka and integration testing, and built in exactly one semantics that are built in for this purpose. However, there's one thing that is, some people might say this, it's a bad thing, it's a good thing, but it is only Kafka-centric. Now, when you're going to be using Flink, this is where you need to deal with massive amount of state, places where you're running cluster, and you need to use this state all the time. Like you're running like a big windows of aggregating this that will create some local store. When you need to deal with not only Kafka, Kafka is not only option for you in this particular case. You might have files. There's a bunch of different examples how you can, using Flink, you can do CDC. You don't have to do CDC through Kafka. In Debezium, Flink has its own. So you can have something from Kafka, something from CDC, and you do joins. There's no distinction between batch and stream. The unified API is there, and it's quite nice. I'm not even covering here, so there's some other frameworks that can integrate with some AI bits. We're working on something like this at Confluent. There is a complex event processing framework that is built on top of Flink, so you can use this type of jazz. Flink can also be used with Python, and through PyFlink, you can submit some of the jobs or define jobs in Python and interact with Flink cluster. If you are interested in these things with stream processing, Kafka, all things like this, we actually, in May, will have the event called Current, formerly known as the Kafka Summit London. And if you have a story to tell about Kafka, stream processing, or something like why Viktor's presentations suck and mine better, please submit your talk. But if you will submitting this particular talk, I will be in program committee and probably will vote you down. And with this, as always, have a nice day. I will be available here until the end of conference. I'm available, if I'm looking big, it doesn't mean I'm not approachable. You can ask me any question about Kafka processing. I know quite a few things if you are trying to find the answer. And I think we don't have a time for the questions, but like I said, I'm available. I will take off my laptop and will be available to answer any questions. you.